Well, today we're going to start talking about the last of the functional groups that we've kind of avoided at this point. We've mentioned esters along the way, but now we're going to actually look at how we go about making them and how we name them properly. So esters, hopefully you remember, are our RC double bond O R group. So they're like a carboxylic acid, but instead of having a hydrogen, we have them connecting to another carbon, so they sort of fit in the middle of a carbon chain. These compounds have particular properties, so they are quite volatile, which means they turn into a gas easily, and they have strong aromas. So they tend to be used in compounds that require sweet smells or flavours, so things like flavouring agents or perfumes, synthetic flower smells, room deodorizers and those kinds of things. So they're used anywhere that you can kind of imagine that you want a fruity or florally sweet kind of smell. So, key thing here is that when we make esters, we actually are going to bring two other hydrocarbon molecules together, an alcohol and a carboxylic acid functionality. We're going to bring them together and in a condensation reaction. So we say that esters are products of condensation reactions, which is a new reaction for us to learn. But if you've done bio, then you'll understand that biopolymers like DNA and carbohydrates and proteins are all products of condensation reactions as well. So during this reaction, when we bring the alcohol and the carboxylic acid together, what we end up with is producing a molecule of water. Okay, so we bring two things together, we produce a molecule of water, and it's important to remember that this molecule of water is produced as a byproduct. Okay, and it is often referred to in questions as the inorganic byproduct of the reaction. Okay, so when we form the esters, these, as you can notice here, we've got a polar group with the carbonyl and down into this oxygen here. So this is our ester functionality, okay, the ester functional group. So it can form dipole-dipole bonds, but we've got these large hydrocarbons on either side with non-polar characteristics. So they tend to do what we call oil out, which is they will form an oil liquid on top of a water solution rather than being soluble in water. So let's have a look at these. These are a couple of examples that we can see here. So we can see here that we have the ethyl cinnamate. So this isn't using IUPAC naming, but we can see here that we have the ester functional group is highlighted in red here with our two oxygens and our oxygen here. And then we have this bit here. And we can see that we have 2 carbons, which gives it its ethyl name. And then this carbon chain, so back from this carbon all the way down here, is what gives it the cinnamate name. Okay, and this is what the actual flavour and smell of cinnamon comes from, this molecule here. Benzyl acetate, this is a space filling model, so it looks a little bit different, but we can see that we've got this ring system here, which would be a benzene, and then we can see we've got the 2 oxygens of the ester there. And then down to our normal skeletal formula, we've got the zigzag carbonyl into our ester and our double bond here, and this is what we call allyl hexanoate, and this is a pineapple kind of flavour. You don't have to name esters with a double bond in them. We just name normal esters. So let's move on. Typical esterification, so we call the condensation reaction to produce an ester an esterification reaction, okay? And if we look at ethyl ethanoate, we can start to see how this goes together. So we heat a mixture of ethanol, C2H5OH, our alkanol or alcohol functional group here, the hydroxyl, and ethanoic acid, so our C double bond OOH here, the carboxylic acid functional group, in the presence of an acid. So we have to have an acid catalyst for this, and it's always concentrated H2SO4. So this is our acid catalyst. And it tends to be, you'll see this form of H2SO4 written as CONC, C-O-N-C, which is just short for concentrated H2SO4, which is the most concentrated that we can get, around 10 molar. So what happens is if we take the ethanol and the ethanoic acid in the presence of H2SO4 and give it a bit of heat to kick the reaction along, we will lose the OH of the acid group and the hydrogen from the hydroxyl group to produce our water, and a new bond is formed between the oxygen and the carbon of the carbonyl, so a new bond formed. Okay, that new bond will now give us the ester functional group that we have here, the ester link. So what was attached to the alcohol is on the left here, and what was attached to the carboxylic acid is on the right, and we have our water byproduct. Okay, so let's have a look. The general reaction for an esterification is the R group, remembering this is any variable carbon chain, carboxylic acid, plus a different carbon chain, can be the same, but we use R prime to denote that it is something different to this one. With our alkanol group, we'll give the RCOOR. This is the general form of our ester functional group and water. So when we write it out with showing the bonds to the carbon, between the carbon and the oxygen, we get the RCOOR in our general formula. So the key things to pay attention to when this is going on is that you need to know which bit's coming from your alcohol and which bit is coming from your carboxylic acid. The R group that goes into the C of the carbonyl is always from the acid, so this one here. And then the R group that goes into the single oxygen is from the alkanol. Okay, so we've got this alcohol group here is what has gone into form this single bond to the oxygen. It's important to know this because we need to know how to name it. So the group that goes into the single bonded oxygen from our alcohol gets the -il suffix, in this case ethyl because it's 2 carbons long, and then the chain coming out from the carboxylic acid part of the molecule, including this carbon from the carbonyl all the way out, in this case it's 2, so it's eth, gets the -anoate suffix. So let's try some of these. So if we have a look here, we have methanol. Sorry about that. We have methanol plus, this is our carboxylic acid, and it's 1, 2, 3, so it's propanoic acid. And when we put these together, I'm going to get the I'm going to be write it in a combination of semi-structural and structural just for ease here. CH3, this is my alcohol, so I'm just going to go to the O, into the carbonyl, and then out to the rest of my molecule, which is this is being annoying today, CH2, CH3. So when I come to name it, it's the part from my alcohol, which is just one here, so that will be methyl. And then this part here will be 1, 2, 3 prop, so it's propanoate. Have a pause of the video and try the other two, and then watch the explanation on how to get the names for those. Okay, hopefully you had a go and you have come back. So let's see what we've got. 1, 2 here, so this is ethanoic acid. And then we've got 1, 3 in here, so that's 4, 5 for the alcohol. So this is pentan 1-ol. Okay, so now we've got, it's pentanol that this has come from, so it's going to be CH3, CH2, 3CH2O, C double bond O, CH3. So this is ethanoate, and this will be 3, 4, 5 pentyl. So pentyl ethanoate. Last one, again, here we have methanoic acid, the smallest of our carboxylic acids. 2, 3 carbons here, so let's draw it out. Then we have into the O, and we'll have H here for the last one here. And that's our alcohol into our acid. And so now this will be methanoate because it's just a single carbon. Sorry about that. Methanoate. And then this one's a little bit tricky. So we've got 1, 2 for our chain, and then we've got a methyl coming off it. So in this case, it's going to be 2 methyl ethyl methanoate. Now you don't have to naming branch esters not in standard level course, or higher level for that matter. It's just one to see if you could figure it out. But you won't get anything more difficult than these kind of ones here. Okay, so if you can figure out what the alcohol is and what the acid is, then you should be able to name an ester. I'll give you some practice and hopefully it will become second nature. So what this means is that we have a whole series now of different reactions that will be able to be interconverted with each other to form different functional groups. We will do a mind map in class to bring these all together, but hopefully you're starting to see now that we can go back and we could start with an alkene, form an halogenoalkane, and then form an amine or an alcohol. We can oxidize that alcohol to form our carboxylic acid, and from there we can condense the two to form an ester. But there's a number of different molecules now that we can come to put together. As you go through and answer exam questions, you will be given schemes with different boxes missing, getting you to fill in the molecules or getting you to fill in the reagents for these. So it's really important you make good study notes on this because it is quite a lot to remember, but hopefully you're starting to see how it links together, and that's making it a little bit easier to remember. Okay, so that's it for our pathways. There is only one more part of organic and then we're done.